Hello and welcome to Caltech's 2025 3-Minute Thesis competition. My name is Stephen Davison and I'm the interim University Librarian at Caltech. The Caltech Library is delighted to partner with the Graduate Studies Office and Theatre Arts at Caltech for this event. Before we begin our program, I want to acknowledge and offer our respect to past and present Gabrielino, Tongva and Kizh people for their unceded ancestral lands, including the LA Basin upon which Caltech sits today. We invite you to honor the Gabrielino Tongva with us and to acknowledge the Native, First Nations, and Indigenous peoples who have stewarded the lands which you and your hometown may occupy. Originally conceived by the University of Queensland in Australia, and if I have an accent, that's because that's where I'm from too, the 3-Minute Thesis competition challenges Caltech graduate students to explain their research in an engaging and clear 3-minute talk intended for the non-specialist audience. The ability to clearly communicate both the methods and results of science research may be more important now than ever before. As a society, we're facing numerous issues of critical social and environmental importance, and an informed and thoughtful public is essential to our ability to solve them. Given Caltech's prominence in the science and engineering communities, it's of enormous value to Caltech graduate students to have the opportunity to practice communicating their science in ways that will resonate and inspire. We received many submissions from our grad students, and we have chosen 13 finalists to present their research today. Thank you to our preliminary judges, Kathy Johnson, Philip Jaffe, and Olivia Warshaw from the library for their work in choosing the finalists from the many applicants. This evening, our 13 finalists will be competing for 4 prizes, made possible by the generous support of our sponsors for this evening's event. And those sponsors are listed on the screen: EBSCO, TEMA, AIP Publishing, American Chemical Society, IOP Publishing, Annual Reviews, the Royal Society of Chemistry, the Society of Photo-Optical Instrumentation Engineers, SPIE, Springer Nature, and Wiley. Through their generosity, our finalists will be vying for a $3,000 first prize, a $2,000 second prize, a $1,000 third prize, and a $500 prize for the Dana Roth People's Choice Award. Representatives from each of these sponsors are attending the live stream or in person this evening, and I would like to thank you all for your support of our Caltech graduate students and science communication in general. If you would like to support the library, please visit library.caltech.edu or follow the QR code on the screen. That's a code for giving money, right? There are lots of other ways to support the library too, and one of them is actually being here this evening, and we really appreciate that. I would like now to introduce you to our Master of Ceremonies, Prien Brophy. Prien is the director of the Caltech Theatre, story coach at the Jet Propulsion Laboratory, co-creator of Credible Messenger Training, and a Fulbright Scholar at the Indian Institute of Technology, Gandhinagar. He facilitates scientific storytelling workshops, is a 25-year veteran actor in the film, television, and theatre industry, and builds global and local collaborations, most recently with the City of Glendale, JPL, and the Getty for the co-creation of Earth Data, the musical. Take it away, Prien.
Hi, everybody. Good morning, good afternoon, good evening. First of all, how many grad students are here? Wow, look around and look at all the grad students. Any undergrads? Oh, you love it? I'm over here, good. Any staff members? Nice, supporting, I love that. Faculty? Coolio. Who am I missing? And all the folks online, too. Fantastic. I'm so happy that you were here. I'd like to now introduce our judges. We have these awesome judges. they were going to select the first, the second, and the third place winners, and you, the audience, will be voting for the People's Choice Award, which is called the Dana Roth People's Choice Award. So our judges right here, Dr. Christian Briney. Yay, give it up for her. Kristen is Caltech's biology and biological engineering librarian. She has a PhD in chemistry and a master's in library and in information science, both from the University of Wisconsin-Madison. Kristen is the author of the books Data Management for Researchers and Research Data Management Workbook, and conducts research on data management and sharing. Give it up for her. Dean Daryl Peterson, this is your third year doing this? Second, third year doing this? Something like that? Good to have you back. Daryl is the Associate Dean of Graduate Studies here at Caltech. He received a BA in Communication and a Master's in Education in Counseling Psychology, both from James Madison University in Harrisonburg, Virginia, and a PhD in Educational Leadership from Iowa State University of Science and Technology in Ames, Iowa. Very cool. Daryl has over 28 years of experience in higher education and student affairs and has worked with both undergraduate and graduate students at a variety of institutions from coast to coast. Here at Caltech, Dean Peterson coordinates new student orientation and provides a support for graduate students in crisis and serves as a member of the CARE team. Give it up for Daryl. Nice picture. All right, Dr. Suzanne Hall is next. She directs the Caltech's Hickson Writing Center and is a teaching professor of writing in the Division of Humanities and Social Sciences. Her teaching focuses on helping undergraduates make a successful transition to college writing, as well as on helping students explore how and why scientists and engineers communicate about their research and their lives. Her research interests are broadly in the teaching and learning of writing, with specific interest in writing in the disciplines, all of them, generative AI and ethics. Let's give it up to them. And this year we've got Dr. Lucy Jones with us. She's a meteorologist. Seismologist. Did I say meteorologist? No. Oh, there you are. Hi. Dr. Lucy Jones is a seismologist. Thank you. Founder of the nonprofit Dr. Lucy Jones Center for Science and Society that supports the application of science in the creation of more resilient communities, and a research associate in the seismological laboratory at Caltech. She is the author of The Big Ones, How Natural Disasters Have Shaped Us and What We Can Do About Them, published by Doubleday in 2018. Creator of The Great Shakeout Drill and co-host of the podcast Getting Through It. Yes. She is also a musician, performing on the viola da gamba with the Los Angeles Baroque and the SoCal Viols. Cool. And composed music on climate change and nomine terra callens. Cool. Give it up for Lucy. Dr. Lucy Jones. Dr. Dennis Koh is the current chair of the Caltech Postdoctoral Association. He works in chemical engineering with Professor Julie Cornfield, studying non-invasive ocular drug delivery methods to treat refractive errors. He received his PhD from Caltech in 2023, and here he is. Thank you for being with us. Thanks again for this amazing judging panel that we have. They will evaluate the presentations based on the following data points here, the criteria. Number one, the speaker's ability to clearly convey their thesis and the significance of the results to the audience, which is you. Number two, how well the presentation provides context to the research question. Number three, the speaker's stage presence, eye contact, vocal range, pacing, and confidence. Number 4, how well the background slide enhances the presentation, right? Those are the 4 criteria that the judges will be looking at. And now the reason that we're all here, the 3-minute thesis finalists. Let's give it up for them. Our first presenter is Chandler Khan, answering existential questions with radioactive molecules. Chandler is a 6th-year graduate student, originally from Kansas, but completed his undergraduate studies at Northwestern. Outside of the lab, he plays French horn in the Caltech Orchestra, enjoys skiing, running in the nearby mountains, as well as taking care of his numerous cacti. Chandler's presentation is titled Answering Existential Questions with Radioactive Molecules.
Why are we here? Not here for my talk. I mean, why does anything even exist? Now, I swear I'm not just being philosophical here. This question actually underlies one of the greatest unsolved problems in physics today. You see, following the Big Bang, our best theories predict that matter and antimatter should have been produced in equal amounts, after which they would annihilate each other and leave nothing. But our presence in this room is evidence that matter does exist, which means there must be something more to our theories. Something such as a new particle or force which prefers matter over antimatter and treats them differently. Something which we say breaks the symmetry between the two. As an experimental physicist, my job is to hunt for these broken symmetries. This is where radium comes into play. Virtually every element on the periodic table is spherical, meaning that they are highly symmetric. Radium, on the other hand, is deformed to look slightly like a pear or an avocado. This asymmetric shape means that radium acts like an antenna for asymmetric physics, causing it to interact much more strongly with those asymmetric, symmetry-breaking physics that we're trying to find. If we use lasers to precisely measure the behavior of radium under controlled conditions, we should be able to see the small effects caused by these new interactions. And if we stick these atoms into a small molecule, the added structure makes them thousands of times more sensitive to new physics than radium on its own. These small molecules are what we wish to study. But now we have a big problem. How do we work with the radioactive element that is so dangerous that it killed Marie Curie after she discovered it? We definitely won't be able to use that much, partly for these safety reasons, but also because certain sources of radium can cost nearly $600 million per gram. Because of these challenges, only one experiment has ever studied a radium-containing molecule in our way, and that was at the Large Hadron Collider in an experiment that takes up more space than this massive lecture hall. And even then, to detect their molecule, they have to destroy it, meaning they can't use it for new physics. This is why I designed and built an apparatus that fits on a tabletop and preserves our molecules after studying them, in addition to using around 10,000 times less material than our experiments typically use. But less material means smaller signals. So to even have a chance of observing these molecules, my team and I had to get creative. We brought in tools and knowledge from basically everywhere. Some highlights including old radium-painted watch hands, a 50-year-old laser from eBay, and even chemistry inspiration from the Journal of Dentistry. And after solving challenges that our field had never seen before, we were finally able to characterize 3 of the first ever radium-containing molecules, tripling the total number known to physics today. Now we're laying the groundwork to use them in an experiment to search for broken symmetries, hopefully bringing us closer to answering that age-old question of why we're here. Thank you.
Thank you, Chandler Khan. And now presenter number 2, Tony Rodriguez. Tony is a final year PhD student in astrophysics working on the discovery of binary stars, particularly those containing one compact object in the multi-wavelength sky. He is an NSF Fellow and Ford Foundation Fellow, working with Professor Sri Kulkarni. Previously, he studied physics at Stanford University and hails from the agricultural city of Salinas, California. His family originates from rural central Mexico, and Tony has given public talks in astronomy fully in Spanish with the Caltech Astronomy Outreach Group. Tony's presentation is titled The Diverse Physics of Binary Stars.
Did you know that the majority of stars in the universe exist as a binary pair? Humanity benefits from the study of binary stars since they serve as extreme physical laboratories, unlike anything we can produce on Earth. For instance, mass transfer in binary stars, as you can see on the upper left, is an example of an extremely efficient energy conversion process, more efficient than anything on Earth, even beating out hydrogen fusion in the sun. In my PhD, I asked the question, how low can mass transfer go and still be seen? Mass transfer is an extremely energetic process, creating powerful X-rays, just like the ones that vaporize cancer cells on Earth. I focused on the most abundant of these extreme binaries, those that contain a white dwarf star. White dwarfs, the blue-white star you see on the upper panels there, are so dense that even a teaspoon of their material weighs as much as 5 cars. However, finding such systems is a true needle in a cosmic haystack problem. So I developed a novel, multi-wavelength approach and took the biggest X-ray and visible light data sets ever created in astronomy to find these systems. I was successful and discovered dozens of new systems, finding that mass transfer is lower than previously thought, but remains just as efficient. Next, I addressed the question, the mystery of white dwarf magnetism. On Earth, our magnetic field literally keeps us alive. It shields us from the solar wind, which would otherwise wipe out our atmosphere. On white dwarfs, magnetic fields can be so strong that they funnel material down, as you can see on the upper right. Recently, it's been proposed that actually white dwarfs and Earth generate these fields in the same exact way, through rapidly spinning fluids in their cores. My multi-wavelength approach discovered a key prediction of this theory by finding a rapidly spinning, extremely magnetic white dwarf gaining mass from a companion. And now, I'm looking toward the radio sky. In the last few years, we've been finding radio signals from space, pulsing, much slower, thousands of times slower than previously seen. And that was a mystery as to what they were. I knew that we needed a multi-wavelength approach, so I pulled out the world's biggest visible light telescope and pointed it right at one of these sources to learn what it was. That's only something I could do as a grad student here at Caltech, by the way. Much to my surprise, I jumped out of my seat when I found out that this was indeed a binary system containing a magnetic white dwarf. I hope I've convinced you that in order to study the most extreme physics that we will one day harness here on Earth, it helps to look to binary stars and to see things in a different, multi-wavelength light.
Thank you, Tony. Tony Rodriguez. And now presenter number 3 is Pierro Chapin. Pierro is a 6th-year PhD student in physics, advised by Oscar Painter. His research combines aspects of physics, engineering, and material science to build devices that use quantum physics for new and exciting applications. He is not just a scientist in his free time. Pierro enjoys playing the drums, surfing, and petting his dog. Pierro's presentation is titled Building Blocks for the Quantum Future.
We are in the wake of a computing revolution. We are taking computers to the extremes of nature, to temperatures colder than outer space. At these extremes, quantum particles come to life, and they behave in ways that defy the physics of everyday life. We are building machines that can control these quantum particles and make them do calculations for us. We call these machines quantum computers, and they could solve certain problems in minutes that would take a traditional computer longer than the age of the universe. Now, the problem is, no one has built a good one yet. I mean, a quantum computer is a complicated machine, and we're learning how to build it piece by piece. And there's one piece in particular that's missing. That's what I want to talk about. I introduced you to the humble transducer. It's a device most people know nothing about, and yet it is the underpinning of the modern-day internet. A transducer converts the electrical signals from your phone into light. Now, why is that? Because internet cables are special. They don't carry electricity, they carry light. Because light travels faster and farther than electricity can. A transducer bridges the gap between computers and the fiber optic cables that give us high-speed internet. Without one, high-speed internet as we know it would not exist. So here is the problem. There is no transducer for quantum computers. The technology is just not good enough. So while we've made progress building quantum computers themselves, we don't know how to connect them with each other. That's a huge problem. I mean, think about it. What good is a computer if you cannot connect it to the internet? That's where I come in. I've spent my PhD developing a quantum transducer. I've shown it for you here on the screen. It's a tiny device. You could fit about 300 of them on the tip of a human hair. We manufacture it on a chip, like the one in your cell phone, wire it up to a quantum computer on one end, a fiber optic cable on the other, cool everything down to cryogenic temperatures. That's where the magic happens. Over the years, with breakthroughs in engineering, material science, we have shown that this device passes the key performance metrics to connect electrical quantum computers with fiber optics, just like the modern day internet. So this opens up a door of possibilities. We could now take smaller machines, connect them all together, and make a giant quantum computer, the kind that's suitable to tackle some of the world's hardest problems. A quantum transducer is a key building block for this, and we hope that this tiny device could play a big role in our quantum future. Thank you very much.
Thank you, Pierro Chapin. And our next presenter is Elena Prien. Elena is a third-year material science graduate student in the group of Professor Brent Fultz, who's here today. Her research focuses on magnetic materials, particularly those with unusual thermodynamic properties, such as magnetocaloric and invar materials, the latter of which she will be presenting today. Originally from the UK, Elena completed her MSci in physics at University College London, where she first became interested in the intersection of materials science and physics, a passion that ultimately led her here to Caltech. She is especially committed to sustainability, serving as co-chair of the Graduate Student Council Sustainability Committee and as the graduate student rep on Caltech's Sustainability Advisory Council. After her PhD, Elena hopes to pursue a career that bridges materials innovation and sustainable technology development. Elena's presentation is titled The Entropy Mystery of Iron 68 Palladium 32, Solving the Puzzle of Vanishing Expansion.
Well
Very
done.
good.
Thanks so much. All right. Picture this, a century-old scientific mystery, a peculiar metal that simply refuses to expand when it's heated. Not broken, just stubborn. To physicists, this was known as the Invar effect, but to us, it was a case worth cracking. In 1896, people first saw Invar materials. These are iron-based materials, but no one could quite understand why they didn't expand. So to crack on this mystery, we looked at a specific type of material, iron 68, palladium 32, and we used a very common piece of equipment in the lab, a synchrotron. No, I'm joking. What we did was ramp up the pressure. We wanted to see if the trick wasn't just in the chemistry of this material, but what would happen if we changed the pressure as well. So what we did is we ramped it up to 18 gigapascals. That's 180,000 times atmospheric pressure. You could say we were putting the material under intense interrogation. Sorry. What we found was really interesting. Between 4 and 11 gigapascals, the thermal expansion of this material went away, just like the original material, Invar, found back in 1896, but now under pressure. So why did this happen? Well, to look at this a bit deeply, we looked at a thermodynamic clue, a Maxwell relation that let us split the expansion into two main suspects, magnetic entropy and vibrational entropy. As the pressure rose, magnetic entropy increased. The spins became more chaotic, just like if a wasp were to fly in here and everyone tried to scramble out the door. And vibrational entropy, at the same time, drops. And at just the right pressure ranges, these two effects cancel out. Zero expansion. Balance. Now, here's where it gets really interesting. The increase in magnetic entropy is somewhat expected. I mean, we're going through a magnetic transition in the material when we apply pressure, and so a change in entropy is expected there. But the way that the vibrational entropy falls to meet that increase, that's not trivial. That was the twist in the tail. So especially at 11 GPa, there's a massive hike in the magnetic entropy, but the vibrations push back. The vibrational entropy falls to exactly counteract that. This shows us that there's more than what meets the eye in this material, an interaction between spin and vibration, what we call spin-phonon coupling. It tells us that sometimes in science, the clues were there all along, just waiting for the right lens and the right pressure. Thank you.
That was Elena, Prien race. Our next presenter is Xang. Jayu is a fifth-year PhD student in neurobiology at Marcus Meister's lab, studying learning and memory through the lens of animal behaviors. Outside the lab, she is better known as the bird lover and avid birder, wildlife photographer, artist, and author of the biweekly wildlife column for the California Tech newspaper, where she shares stories and photos of campus creatures from coyotes to woodpeckers. This winter, she designed and taught an undergraduate tutorial, Biology 23, the Ethology of Learning. Jayu's presentation is titled Mice in the Manhattan Maze, a tale of rapid learning.
Imagine being trapped in a dark maze, looking for water while a wicked graduate student keeps changing the rules. This is the tale of a small but clever mouse and its battle for survival. Once upon a time, a clever mouse lived happily in its cozy home with abundant food and water. But a wicked graduate student, jealous of the happy mouse, caused a spell and drained the water. Thirsty, the mouse ventured out into a pitch-dark maze, a single long tunnel with a hole leading upward. Bravely, it climbed up through the hole, and look, it found the water at the end of the maze. Angered by the mouse's success, the wicked graduate student changed the maze from 1 hole to 9 holes. The once simple path became a zigzag labyrinth with every single hole leading to uncertainty. But the mouse hesitated, retraced the steps, but pressed on. Its first run took a few minutes, but after just a few rewards, it could do it in just 20 seconds. Desperate, the wicked graduate student locked the mouse away, hoping it would forget about the maze overnight. But on the next day, it remembered the route just as well. Eventually, even if the student kept changing the mazes, the mouse could solve the maze with ease. Using its previous experiences in the 9-hole maze, it could now solve any type of 9-hole maze. So, with its intelligence, the mouse trapped the wicked graduate student in a puzzle, who spent the next 5 years trying to figure out why mice solved mazes so fast. So, this is the tale of mice in the Manhattan Maze, a maze structure named after the grid structure that looks like the city streets in the Manhattan Island. And who was this wicked graduate student? Me. Using this setup, I studied rapid learning in mice and noticed that they could just use a few reward experiences to learn a sequence of 9 turns. And that is a phenomenon called few-shot learning. We also found that the mice can memorize the maze overnight and generalize its knowledge to new mazes. This setup also helped us do cross-species comparison, including human participants. And for your information, human participants did very poorly in a virtual maze. So we also used this maze to train data and for a very efficient way. So next time, when you think about troubling a mice, do think twice. Thank you.
Thank you. That was Yayu Xang. Our next presenter is Ye-Chan Lim. Ye-Chan is a third-year PhD student in applied physics. He earned his bachelor's and master's degree from Seoul National University in Korea and came to the United States with support from the Korean government scholarship program for study overseas. His research focuses on how to engineer thermal emissions to make them practically useful. Lately, though, his personal focus has shifted to a new challenge, figuring out how to fund an engagement ring and the perfect proposal. Ye Chen's presentation is entitled Engineering Thermal Radiation for Reversing Global Warming.
Thank you. You might have seen the headlines saying global warming has gone too far, that even with our best efforts, it may no longer be reversible. It's a pretty depressing thought, isn't it? But today, I want to offer you a different perspective, one that gives us hope. Many of these reports focus on carbon emissions and their predicted impact on the future. But at the core of global warming is something more fundamental: heat. For decades, heat has been treated as unavoidable waste, a byproduct we couldn't do much about. And despite its central role in climate change, controlling heat remains one of science's greatest challenges. But what if we can control heat as easily as we control electricity? This is where my research comes in. Heat is everywhere. It radiates from the sun, the earth, and even from our own bodies. But unlike electricity or light, heat is messy. It spreads out in all directions, making it hard to harness. This difficulty comes from the nature of thermal radiation. Inside any object, internal energy causes charges to oscillate randomly. And these random oscillating charges emit thermal radiation. But because the oscillations are random, the radiation spreads out in every direction. But what if we can make that chaos work for us? Just like a laser cavity turns random light into a focus beam, we can design a structure that channels these random thermal fields, guiding them to resonate and emit in a single specific direction, creating a coherent thermal beam. This is a shift in how we think about heat. Until now, most efforts focus on creating surfaces or using special materials like phonon-platonic materials that only work at narrow wavelength ranges. But my approach shows that the coherence and directionality can emerge from the cavity design itself, unlocking broadband performance and I'm sorry about that. And flexibility in material choice like silicon or germanium that are readily available. The concept is simple, powerful, and even scalable. And once we can control heat in this way, the possibilities are enormous. We can direct waste heat from power plants straight into outer space, and we can reuse that heat as energy and keep buildings and cars comfortable with little to no electricity. And even that hot smartphone in your hand, we can cool it more efficiently. By learning to control and recycle heat, we can reduce energy waste, slow down global warming, and maybe, just maybe, start to reverse it. Thank you very much.
Thank you. That was Ye Chan Lim. Next up is Harula Balyaka, is a fourth-year PhD candidate in environmental science and engineering at Caltech, working with professors Paul Wenberg, John Seinfeld, and Rick Flagan. Her research broadly focuses on studying the mysteries behind the elevated particulate levels in Los Angeles. Despite decades of air quality regulations, Harula is also the student lead for Phoenix, an air quality monitoring network deployed in and around the burned areas of Altadena following the recent Eaton Canyon fire. She is from Greece and holds an engineering degree in chemical engineering from the University of Patras in Greece. Outside of research, Harula enjoys dancing, cooking Greek dishes, and discovering what it means to be living the American dream. Harula's presentation is titled Trace Elements, Big Impact, Unveiling Air Pollution Sources for Cleaner Communities.
So you know when you're on the 9th floor of the Caltech Hall Library and you see the beautiful mountains? Well, in the 70s, the air in Los Angeles was actually so bad, those mountains would have been completely hidden by a blanket of smog. And while yes, we have made tremendous improvement in air quality over the past few decades, air pollution in California still persists despite regulations. Why is this? Well, that's where my research comes in. For my thesis, one of my focuses has been looking at trace elements in the atmosphere. Now, they're called trace elements because they can be found in exactly that, trace amounts. So you might be wondering, well, if they're found in such small amounts, why do we even care? And the answer is that these elements are valuable and that they provide a fingerprint, a tracer, if you will, for the sources of air pollution. And these elements were actually found to be incredibly insightful when the Eden Canyon and Palisades fires erupted earlier this year. Because just days after the fires started, concentrations of lead, which is a toxic air contaminant as well as a trace element, was found to be 100 times higher than typical baseline levels in the fine airborne particles. So even I had to double check and make sure that this made sense. And the truth is that these fires were not typical wildfires, but in fact urban firestorms, where pipes, vehicles, plastics, and even the structures themselves became the fuel. So when looking at urban fire emissions, finding toxic metals like lead is not unusual, especially in our case, when a large fraction of the structures affected by the fires in Altadena were much older and were built when leaded paint was still common. So you can imagine, if we found toxic metals in the air during the fires, then those must have deposited on the ground. So what does that mean when cleaning up the debris removal? It's likely that this dust can get resuspended, meaning it can get kicked back up into the air, exposing the people all over again. And that is why we created Phoenix, a post-fire air quality monitoring network of over 25 sensors in and around the burned areas of Altadena. We were able to successfully create this grid of sensors within 1 month by partnering with Altadena and Pasadena community members. And this is community science at its finest. And I'll end with this, some food for thought. This is a snapshot in time of the concentrations of larger particles indicative of local dust events. And you can see there's a hotspot marked in red, marked as unhealthy. Now, is this dust from the mountains or is it from the debris removal? I'm determined to find out. Thank you.
Thank you. That was Harula Balyaka. Our next presenter is Mike McKon. Mike is a 6th-year PhD student in planetary science, working with Heather Knudsen. His research focuses on characterizing small, rocky planets beyond our solar system with telescope observations. He grew up in New York and received bachelor's degrees in physics and astronomy from the University of Maryland College Park. Mike's passion for astronomy has taken him from trying to see past light pollution with small telescopes on the roof of his high school in the Bronx to see past light pollution using some of the largest telescopes on Earth to make new scientific discoveries. In the fall, he will continue his research on rocky planets as a Carnegie Research Fellow at the Earth and Planets Laboratory in Washington, D.C. Mike's presentation is entitled Searching for Oceans and Volcanoes on Distant Planets.
Have you ever looked at the stars and wondered if there's life on distant planets? Humans have asked this question for generations, but now, thanks to advanced new space telescopes, we may be the ones that finally get an answer. How? Well, let's imagine a planet that passes in front of its host star, and light from the star filters through the atmosphere of the planet and reaches us. By measuring which wavelengths of light are absorbed in the atmosphere, we determine which molecules are present. If the molecules there are only produced by life, then we found our aliens. Now, the bad news about this kind of search for aliens is that of the thousands of planets that we've found beyond our solar system, very few of them are rocky worlds that have a surface to stand on and an atmosphere to protect from space. And none of them so far have confirmed liquid water or active volcanism like the Earth. We know that life is abundant in oceans on Earth, and even for the harsh environments of volcanoes, some bacteria find it enjoyable. So those might be two good things to look for. And thankfully, the James Webb Space Telescope can detect signatures of these molecules in the atmospheres of these planets. But first, we need to know which planets to point the telescope at. That's my thesis. I measure the water content and the internal heating rates for rocky planets. By observing multiple planets in systems that have close orbits, the gravitational forces pull and tug between planets, which changes the time when they pass in front of their star. By observing these orbital variations driven by gravity and how much light the planet blocks when it passes in front of its star, I measure the masses and the radii, and therefore the densities of these planets. Modeling the orbital variations also tells me how much the interiors of the planets are distorted by gravity, which can produce internal friction and volcanic activity. I've applied these techniques to dozens of planets and found 3 so far that have precise density measurements which match a composition made of rock and water. These planets are not so dense that they are made almost entirely of metal and rock, like Mercury, but they're also not so puffy that they have a thick atmosphere which blankets the planet and makes it so that any surface is too hot to have liquid water. As Goldilocks would say, they're just right. I've also found 2 planets that have significant internal heating from this distortion, and that can drive friction in the planet, which produces volcanic activity. The James Webb Space Telescope can confirm the signatures from these things, but we need to observe the planets first. Several of the planets I've characterized will be observed by James Webb, one as soon as next month, which means that maybe someday very soon, you'll be able to look at a specific star with a specific ocean or volcano planet and wonder who might be there looking back at us.
Thank you. That was Michael Greck McKeon. Our next presenter is Dion Kersner. Hannah is a graduate student in geobiology. Her work investigates biological processes that remove greenhouse gases from the atmosphere. She hopes to improve our understanding of the two-way relationship between climate change and biology. Hannah is passionate about advancing educational equity, and in her spare time, she likes to read and play music. Hannah's presentation is titled Understanding Environmental Change Through the Diaries of Trees.
Imagine you wanted to know the weather in London on August 1st, 1917. There are a couple ways you could find out. You could go to the archives of newspapers, like this article that wrote that 3.22 inches of rain fell. Or you could look at personal archival documents, like this journal entry from Lavinia Talbot, who wrote that day, "Sweeps of drenching rain all day." Whoa, whoa. If all you wanted to know was the exact amount of rain that fell, the newspaper article would be a great source. But what if you cared about how that rainfall affected the world around it? In that case, we can learn a lot from diary entries like Lavinia Talbot's. Dendroclimatology is the study of using tree ring measurements to reconstruct past changes in climate. These measurements provide really important information about climate change on Earth, and making these measurements is not so different from reading a diary. The chemical composition of the wood is reflecting the environment where the tree grew. But tree rings are also like diary entries in that their chemical composition is not a direct report of the climate, it's actually a reflection of how the climate affected the tree. Traditional measurements can't separate out the climate signal from its effect on that specific tree. And so researchers are limited to choosing specific tree species and research sites where they know that their climate signal of interest is expected to be especially strong. And if the tree's response is mixed in with the climate signal, it's treated as noise. But a tree's response to climate change is not just noise. It's important information about how plant health and function responds to environmental change, and it can give us a fuller picture of what our ecosystems might look like in the future. So in my research, I have developed a new method to measure tree rings with higher chemical resolution. For the first time, we are able to measure tiny tree ring samples, chemical changes at individual atomic positions within the cellulose molecules that make up tree ring wood. And it turns out that some of these atomic positions, their chemical signatures are more reflective of environmental changes, like precipitation, where other of these positions are more reflective of the tree's metabolic response to those changes. By measuring different tree types grown in different conditions, we've found that we're able to measure environmental changes like soil moisture and temperature, as well as the tree's response like root growth and starch production. With this new method, researchers can better understand not just how past climates changed, but also how it affected our ecosystems by reading the diaries of trees.
Thank you. That was Hannah Dion Kersner. Our 10th presenter is Victor Vescu. Victor is a third-year PhD candidate who uses numerical modeling to study both natural and human-induced earthquakes. He is an avid rock climber and mountaineer and enjoys practicing improv comedy and playing the piano. Victor is also a Caltech resident associate and assistant manager to Earthquake Sim, a YouTube channel about earthquakes with over 100,000 subscribers. Victor's presentation is titled How Faults Annoy Their Neighbors.
Did anyone feel the earthquake 2 Mondays ago? Last August? Maybe you remember Ridgecrest 6 years ago. A little scary, right? But we've all lived here long enough to get used to earthquakes. We assume they'll hit where they've hit before and be about the same size. Hold that thought. Now jump to Japan, 2011. A magnitude 9 earthquake shakes Tokyo for 6 minutes. Can you imagine 2 of these talks back to back? Scientists are stunned. The quake came from a fault thought incapable of something so massive. How? Back to California. We have the San Andreas Fault. It's more famous than Schrodinger's cat, but less famous than Einstein's hair. The north and south segments, those in red, repeatedly produce large earthquakes. We've tracked them since the 1890s, a blink in geologic time. But between them lies the central San Andreas, seemingly tame. In recorded history, nothing stronger than a magnitude 6. But the rocks say otherwise. Magnitude 7s did happen there long ago. So what's going on? That's what I study, dynamic weakening. When faults suddenly give way more easily once they start to slip. It's how small earthquakes grow large. And faults, I found, are a lot like people. Under pressure, stressed, overheated, or when their neighbors get too close, they snap. When fluids get pressurized, sliding forces ramp up, or friction heats things up, even stable faults can fail. Here's the deal. When shaking on a red neighbor happens, it can irritate its green neighbor, thus allowing dynamic weakening. It's kind of like when your neighbor starts mowing the lawn at 6:02 a.m. on a Saturday. You weren't planning to snap, but here we are. I run earthquake simulations on supercomputers to see when one fault segment could trigger another. And my goal is to see whether dynamic weakening could trigger a megaquake in California's central region. And so far, under perfect conditions, yes, it's possible, but nature is messy. That's why I love adding physical realism to my models, to see when dynamic weakening can and can't happen. Thousands of simulated earthquakes told us that if the slipping interface is thicker than a deck of cards, dynamic weakening won't happen. Small details can flip seismic outcomes. And that matters, because knowing which faults weaken could mean the difference between expecting a magnitude 6 and getting blindsided by a 7.7. So are we safe because it hasn't happened in recorded history? My research says maybe not. Give me your zip code, and I'll check with the fault.
Thank you, Victor Vescu. Our next presenter is Alex Chung. Alex Chung is a PhD candidate in neurobiology, a rock climber, and a proud parent to a 3-legged rescue pup named Nara. Whether he's scaling boulders or exploring the brain's hidden capabilities, Alex is fascinated by resilience in both the natural world and the nervous system. His passion for regeneration was sparked by climbing injuries and a dog who runs like she has 4 legs. Under the guidance of Dr. Viviana Gradinuru, Alex is uncovering how we can harness the power of the nervous system to help the body heal. Because sometimes the key to unlocking superpowers isn't in fiction, it's in our own biology. Alex's presentation is titled Superpowers of the Mind, Harnessing the Nervous System for Regeneration.
How many of you here today still believe in superheroes? Well, I don't believe in Superman or anything like that, but I believe in my mom and all the moms of the world, but most importantly because of how powerful our minds can be. And this is because of case reports of moms being able to lift up whole cars after a tragic car accident in order to save their child. And this is all made possible by the fact that their parental love was so strong to evoke a fight or flight response, which is coordinated by your sympathetic nervous system. During the fight or flight response, did you all feel that rush of blood feeling as well as adrenaline? And with that, we have the urge to be able to create so much power to overcome obstacles. But I believe that the sympathetic nervous system could potentially hold the power of another superpower, regeneration. And this is because during the activation of the sympathetic nervous system, our immune system changes in how they react to pathogens. This is really important because typically humans are terrible at regeneration. All of you probably know yourself or a loved one who have undergone a serious injury and never healed properly. And this is because our immune system tends to overreact to pathogens and injuries from days when we were cavemen with terrible hygiene. And by over-attacking and attacking the pathogens, we end up destroying our own cells in the process. But I wondered if by activating the sympathetic nervous system to divert all of that energy into fighting off immediate pathogens, maybe we can actually dampen our immune system response so it doesn't react so vigorously. In order to test this hypothesis, I utilized a delivery vehicle which were engineered in the lab. These delivery vehicles can install switches into the neurons of mice. By doing so in the sympathetic nervous system of mice, I could ask the causal question, can the activation of the sympathetic nervous system lead to better regenerative outcome? When I flicked on the switch in mice, which had undergone an ear injury, you can see that right here, you almost don't see a hole remaining in this corner. However, you still see this gaping hole remaining in a mice which their sympathetic nervous system was not activated. Well, the coolest part was yesterday when I was looking into these ears, I saw the growth of new nerves and blood vessels and cartilage. This is exciting, not just because we're looking at ears or whatever, but maybe in the future, we can start looking at regeneration potential for humans, you or your loved ones. And I hope one day we can uncover more potentials of our nervous system, and one day we can all be superheroes.
Thank you. That was Alex Chung. Our next presenter is Sneha Gupta. Sneha is a 4th-year graduate student working in human neuroscience with Professor John O'Doherty. Her research focuses on uncovering the neural and computational architecture that enables humans to set complex goals and plan actions to achieve them effectively. Sneha's presentation is titled An Architect for Goals.
In the movie Terminator, Skynet, an AI agent, goes rogue and decides to wipe out the humans because they're interfering with its goals. Classic sci-fi theme, AI setting its goals and, taking over. It's nice, fiction. But just yesterday, I saw a New York Times article on if AI becomes conscious, should it have rights? I was like, okay, that is crazy. So, but why is it crazy? Because having goals and acting in the interest of their survival is uniquely biological, right? And humans, they don't just set goals to survive. We set goals to thrive. And human brain is the architect for such goals. And I'm a student in human neuroscience studying the master at its work. And how do I do that? I do that by studying its rhythms. And I study the brain rhythms in the fMRI machine while my fellow humans set their goals in a fictional world. And I designed a game where there are multiple projects that you need to choose from, and each project has its own subtasks, and you have to complete these subtasks by collecting resources from the world. And my fictional world is just as cruel as the real world. Just when you're finishing your goal, and I make the resources scarce. So obviously, to succeed, you have to readapt and think of a new way to solve this problem. And that is the process I'm looking at. So see that red region on the top, their prefrontal cortex? By looking at the rhythms in that region, I can tell you exactly what goal my participant is thinking of in the task. And not only that, the rhythms in that region can also tell you what the values for the goals are. The values for the goals go up and down as the goal prospects go up and down in the task. And see that blue region over there in the top? It's called anterior cingulate. And from that region, I can tell you whether there are alternate goals available that are much better than the goal that you're pursuing right now, and that activity ramps up. So I have some key components that enables the architect to construct goals, but it's still the tip of the iceberg. We don't know a lot, and I believe only if we decipher the master's work can we truly be the architect of goals in machines. Now there, don't go judging me. I'm not here to help the AI uprising, but rather I want to enable the AI to set goals to help us align with them and help us achieve our best potential and help us thrive. And that is my goal. Thank you.
Thank you, Sneha. Very cool. Our next and final presenter is Hannah Manich. Hannah is a fifth-year graduate student in the group of Manuel Andres at Caltech. Her PhD work has focused on scaling qubit numbers of single atoms in optical tweezer arrays for quantum computing applications. She did her undergraduate in physics at the University of Illinois at Urbana-Champaign. Hannah's presentation is titled 6100 Atomic Qubits.
Hi, I'm Hannah. I'm excited to tell you today about work that we've done in the Andres lab to scale up the number of qubits, quantum bits, in a quantum computer using atoms. Within the field of quantum science, there's something of a mountain range, if you will, for quantum advantage, where there's many different peaks or goals that quantum scientists have that they'd like to achieve, from quantum simulation to quantum computation, quantum metrology, and even quantum sensing. We heard from Pierro about quantum networking, even. These goals are really just ideas that we have of how one could use a quantum system to accomplish a goal that one cannot do using a classical computer where you just have access to ones and zeros. Scientists also have many different ideas of how to scale these peaks, different paths up them that we're trying out, if you will. From superconducting qubits to trapped ions, neutral atoms in optical tweezer arrays, or even solid-state qubits. But across all of these platforms, as well as all of these goals, there's a common challenge. And that challenge is to scale up the number of qubits that you have while maintaining the controllability and fidelity of these qubits. In the Andres lab, we use optical tweezer arrays that trap single neutral atoms. We focus down these optical tweezers, which are just tightly focused laser beams, into a cloud of cold atoms. Those cold atoms are attracted to the highest intensity part of the light, and once they're there, they undergo something called light-assisted collisions, where they're lost in pairs, 2 by 2, so that if we began with an even number of atoms, we end up with no atoms. And if we began with an odd number of atoms, we end up with a single atom. Scientists have been able to use these optical tweezer arrays to do quantum science on the scale of tens of atoms to hundreds of atoms. But we want to scale that up to actually be able to summit these peaks. We're able to do that using cesium atoms trapped in high-power, far-tuned optical traps. As you can see in this beautiful picture over here, we use 12,000 tweezers, and we're able to trap over 6,100 atoms. Every single atom you see there, every single dot you see there is an atom. And if you zoom in, you can see that we're able to distinguish between the presence of an atom or the absence of an atom with very high fidelity just by looking at the photons that we collect on this camera. Now that we have these atoms trapped, we can move them long distances across the array, which is something that we've done. And you can also make them interact with each other and implement 2-qubit gates, which is something we're working on. But we also want to know, are these atoms actually good qubits? Do they store this information well? We can measure coherence times, T1 times and T2 times. The T1 time tells us how long we can store the classical part of the information, and the T2 time tells us how long we can store the quantum part of that information. And the times that we measure are records for this platform, and they also are very long compared to the time scale of the operation of a neutral atom quantum computer, which gives us hope that in the very near future, we'll really be able to summit these peaks. Thank you.
Thank you. That was Hannah Menich. Please give a round of applause to all of the 3-minute thesis presenters. Woo-hoo! Well, I've been doing this for a few years now, and this is definitely got to be one of the most competitive. Good, right? They're all good, weren't they? Wow, so exciting. We're going to Tommy Keswick. Where are you? Okay, you're over there. You ready? And Kathy Johnson, you're all going to take our judges with you? Is that? Okay. So now we're going to tally the scores. Okay, see, Tommy's coming. Excitement, building. A little bit of momentary. He's collecting the data. He's collecting the results. Daryl is handing it over. Here is Catherine Briney. Everything looks good here. Good. And here's Stephen again.
Thank you, Brian. So that's going to take a while. So I'm going to give a few more thank yous while our judges confer and tally their scores. I'd like to thank our diamond sponsors for this event. First, EBSCO. EBSCO is a proud partner of the Caltech Library and honored to be able to support the 2025 3MT competition. EBSCO provides academic institutions with high quality, essential content and resources for research from thousands of publishers to ensure success for students, faculty, and staff. You can find EBSCO resources using the Caltech Library at library.caltech.edu. And our second diamond sponsor is TEMA. TEMA Chemistry Science of Synthesis provides a critical review of the synthetic methodology developed from the early 1800s to date for the entire field of organic and organometallic chemistry. It is a full-text resource for methods in synthetic organic chemistry and is the largest collection of evaluated organic synthetic methods available worldwide. So we're very grateful to our diamond sponsors and all of our sponsors who've supported this monetarily to provide for the prize money and for the reception afterwards. I also want to thank the 3 communication coaches. So in preparation for their presentations, our contestants were all offered the chance to meet with these coaches. The first, Jeffrey Gold, who's a STEM communication specialist and lecturer in engineering and applied science, over there. Erin Burkett, science writing specialist at the Hickson Writing Center, who's over there somewhere. And Natasha George, STEM writing specialist and lecturer, also at the Hickson Writing Center. So a plug for the center, a very valuable resource on campus. For any of you Caltechers in the audience who want to improve your science communication skills, the Hickson Writing Center is a great resource for our community. You can find out more about their services and book appointments at writing.caltech.edu. I love simple, easy to remember URLs. Brian, do you want to come back and give a plug for the theater arts?
Oh, thanks.
Yeah, that's the
oh,
slide.
there we are. Oh, good.
Yeah.
We're here. Yeah, join us next week. This is our 13th year of doing Mach 33, the science-driven new play festival here at Caltech. We work with new playwrights, new plays that have never been produced before. We work with science advisors. This year, we're working with Joel Burdick in robotics and with Frederick Eberhardt over in HSS and an amazing grad student by the name of Solvin Sigurdsson, who help advise the writers to make sure that we get their science right. So yeah, come. It's gonna be a lot of fun on Friday night. And then Saturday night, we're gonna have the Dementia Doula, which is, you can go to our website and find out more about that. And there's gonna be a reception on Saturday, May 3rd, after we have this really cool conversation. And then there'll be food from Jones Coffee there. Not Lucy Jones Coffee, but Jones Coffee here in Pasadena. And then we'll have our final Dementia Doula, which will be on Saturday night. And if you like storytelling, we teach a class. I teach a class here called Storytelling for Scientists. So June 6th, put that on your calendar. We're going to have a final presentation over in Frautschi Hall, too. So, yeah, thank you.
So we have an opportunity for you to support the library this evening. Last fall, both library and the theater arts participated in the Getty's PST Art and Science Collide program events across Southern California. And I'm sure many of you saw that exhibit here on campus. Crossing over art and science at Caltech, 1920 to 2020, was an expansive public exhibition across 6 campus locations, indoors and out, that wove together the history of science with historical and contemporary art. The exhibition featured displays of over 200 objects. Most are drawn from the Caltech archives and special collections, including rare books, paintings, drawings, photographs, scientific instruments, molecular models, and video. The book of the exhibit, the catalog essentially, which is what you're seeing up here in the video form, features over 300 images from Caltech art and science and 12 essays that explore how institutions like Caltech used scientific representation, art, and architecture to construct themselves and produce discovery and invention. So the catalog normally sells for $65, but special offer tonight, if you would like to buy a copy, we're going to sell it for only $50, and your purchase will support future archives initiatives and exhibits. So now we're going to have some fun. Brian's going to lead that.
Those books are really beautiful if you want to take a look at them outside. They're really extraordinary. So while we wait for the results from our judges, we'd like to play a little game. It's invented by the library's metadata specialist, Mel Ray. Mel, are you here? Mel Ray is awesome. It's called the Caltech Library's favorite game show, Caltech Thesis, or science fiction title. And so here we are. We're going to start out with our first slide, cosmic gold mining. Cosmic gold mining. Does this sound like a science fiction title, or is this an actual thesis? Thesis, am I hearing thesis? Science fiction movie or TV series? Okay, I've got a couple of outliers over here. Okay, good. Cosmic gold mining. Oh, Shreya Anand, 2024. Where are the heaviest elements in the universe formed? The answer may lie in a binary neutron star merger, neutron star black hole mergers, collapsing massive stars, or other explosions. Wow, very cool. Thank you for that. You were right. All right, number 2. Callisto 5. This sounds like a TV series with Arnold Schwarzenegger or something. Callisto 5. Science fiction? Sci-fi? No? Yes? Sci-fi. Yeah, that's what it is. Sci-fi. Sci-fi? Oh, it's a play. Interesting. This could be a new play to do. Young Jem has sat in a space station patiently awaiting the return of his parents for 8 years, with only his robot nanny and the disembodied voice of the station's computer for company. They're made out of meat. Yeah, they are, aren't they? Yeah. They're made out of meat. Oh my goodness, I have no clue on this one. Anyone? Thesis? Thesis. Who says thesis? Raise your hands. Oh, sci-fi. Interesting, kind of evenly matched a little bit here. Oh, Terry Bisson. Short story consists of a dialogue between two intelligent beings capable of traveling faster than light on a mission to contact, welcome, and log any and all sentient races or multi-beings in this quadrant of the universe. Wow. That's really scary sounding. All right, what else we got? Dealing with imperfections on a daily basis. Everyday life here, around the world and in this room. Dealing with imperfections. Is this the thesis? Is it a thesis? Okay. Thesis? Who says thesis? Oh, there it is. Ruizi Cow. Electrical engineering. Optical imaging has gained in popularity, but it's challenging. Solving problems around two forms of blurring, aberration, and scattering could be the answer. Wow, I love that. It's a great title. Deep Dream. Thesis? Sci-fi. Sounds like a Netflix series. Sci-fi. Who says sci-fi? Who says thesis? Okay, I think the thesis are nodding head. It comes at, oh. Intrapramit das. 10 writers imagine the different ways in which art forms might evolve, devolve, shift, and transform in the decades and centuries to come. This is last year. Wow, this sounds kind of cool. Most y'all Indian writers. Oh, very cool. Huh? All right, what's next? Space Legos. It's got to be a thesis, right? Yes. Sahangi Dasanayake. She was one of the presenters here last year. Oh. Woo. Aw, so cool. Space missions require larger and more complex structures, and novel in-space autonomous assembly will make it possible. Yay. Yeah, she was such a delight. What else we got here? Taking the pulse of life. Sci-fi? No? Susan, no. No? Yes? No? Taking the pulse of life. I want that to be a TV series. What is it? Sci-fi. Few sci-fis, okay. How about thesis? Mostly thesis. Interesting. Answer is Guaneng-Dong 2024 geochemistry. Can the evolution of one of the most fundamental classes of compounds, hydrocarbons, help us decipher traces of life and non-life? Wow. That's cool. All right. Chasing After the Wind, of course, that's that new HBO series. Starring Ben Affleck. Chasing After Jennifer Aniston. No. Chasing After the Wind, TV series, right? It's got to be a TV series, right? Or is it a wind harvester TV series? Yeah, I got that. Okay. Thesis. Okay. Answer is, a thesis. Aerospace engineering, David. Oh, cool. Can a drone identify critical flow structures and follow them autonomously as they evolve? In a sense, chasing after the wind for the sake of measuring it. Wow, David sounds like a poet, doesn't it? All right, patterns of chaos. Every day in America. Patterns. trying to figure out all the patterns. Yeah, what are these patterns? Oh my goodness. So this is, it's got to be a thesis, right? Yeah? Bryony's on the, what do you think? Sci-fi? Thesis. Answer is, patterns of chaos. A chaos catalyst has an electrode transmitter receiver planted inside his brain to prevent destroyer space fleet from gaining absolute mastery of the galaxy. Wow, that sounds really dramatic. 1972. Anybody ever heard of this? Nobody. Wow. It's on that VHS bin, you know. And, cool. What else we got? We got more? Carbon currencies. That's right up there with cryptocurrencies, right next to the carbon currencies. It's got to be a thesis, right? Thesis. Answer is, or survey says, Elliott Mueller. Geobiology, novel analytical and computational tools provide new information about the mechanism and rates of organic acid turnover in nature. That's right, he was our last year's winner. That's right, third place. Very cool. He got the $1,000, right? Isn't it cool that you all get the prizes for this? I have to say, y'all did a really good job. You're all super engaging, and I don't know how the judges are going to do this, but you all really delivered it, and it's such a really beautiful. Give it up for them. So good. So good, so good. We got more? We got one more? Mel Ray? Oh, there's more. Ghosts of order on the frontier of chaos. Yeah, well, that's, wow. On the front, a lot of chaos going on in here. Yeah, a lot of chaos. Ghosts of order. What is a ghost of order? Wow, that's kind of intriguing. Ghost of order on the frontier of chaos. It's got to be a thesis, right? No? Jeffrey Gold, what is it? Is that your novel? No, it's not one of them. What is it? Is it sci-fi? Or sci-fi? I have sci-fi. I could one hand for sci-fi. Thesis. God, no one's like a little uncertain here. Okay. Survey says Mark Muldoon, 1989. What kinds of motion can occur in classical mechanics? Looking at the structures traced out by trajectories and phase space may have the answer. Submitted May 30th, 1989. Wow. Before many of you were born in here. Very cool. How are we doing for time? Kathy? You're good? Oh my gosh, you're ready. Okay. And now I'm really excited. I think that you're going to take over now. Yeah? No. Oh, wow. Oh, sorry, my bad. Oh, I didn't read. I got so carried away with this.
Well,
so we're going to, oh, thank you, Brian, for hosting the Caltech. Oh, you say that.
Thank you, Brian, for hosting the Caltech Thesis or Science Fiction game.
Yeah.
Yeah, I'd like to remind you that you can, these theses are all available online. We are actually in the process of digitizing all the remaining theses. So sometime in the very near future, you'll be able to look at all of the theses going back to, I guess, 1920 or so. Yeah, it must be about 1920, I think. Okay, so you take over again.
Okay. I just want to shout out to, like, I see all these folks that were involved with the organization of this. Can we just give it up for Library Services? An amazing job that they made this to happen. Yeah. And also to Academic Media Technology, who are recording it, and down in here, and doing all of the audio. So cool. We will now be conducting the Dana Roth People's Choice. The winner in this category will be chosen by you, the audience, and they will receive $500. Finalists, please step forward and remind our audience of your name and your presentation title. So they're going to come down here with your numbers, letters, I guess, yeah, letters. And you're going to line up on stage by letter. They're going to announce their name, or should I do that? You'll announce your name, the presentation title, and then, yeah, they should shout it out, right? Oh, we've got a microphone even. That's even better. You ready? You all ready? I go, how many are you? Look, this is amazing. Okay, here you go.
I'm Chandler Khan, and my presentation was answering existential questions using radioactive molecules.
My name is Tony Rodriguez. I'm letter B, and my presentation was the diverse physics of binary stars.
My name is Pierro Chapin. My letter is C, and my title was Building Blocks for the Quantum Future.
Hello, everyone. My name is Elena. I guess I'm the letter D. My title was a bit long, so I'm just going to... The entropy mystery of Iron 68 Plane 2, solving the puzzle of vanishing expansion. Yep, thank you very much.
Hi, everyone. I'm Xang, and my letter is E, and my presentation is Mice in the Manhattan Maze, A Tale of Rapid Learning.
Hello, everyone. My name is Yechan Lim. I'm letter F, and my title was Engineering Thermal Radiation for Reversing Global Warming.
Hi, I'm Harula Balyaka. My letter is G, and my title was Trace Elements, Big Impact, Unveiling Air Pollution Sources for Cleaner Communities.
Hi, I'm Mike Greck like McKon, letter H, and my presentation was Oceans and Volcanoes on Distant Planets.
Hi, I'm Hannah Dion Kersner, letter I, and I talked about understanding environmental change through the diaries of trees.
Hello, I'm Victor. I talked to you about how faults annoy their neighbors.
Hi, my name is Alex Jin-hyung Chung, and my letter is K. My title was Superpowers of the Mind. Thank you.
Hi, I'm Sneha Enugu. My letter is L, and my talk's title is An Architect for Goals.
Hi, I'm Hannah Manich. My letter is M, and I talked about 6,100 atomic qubits.
All right, let's give it up for them one more time. All right. Now, audience, I want you to get ready to vote. Each presenter has a letter, which they will be holding up, and they hold it up for you to see. You see all the letters, right? Good? TK, good? All right. Now you're going to vote. And you online, they can online voting too. Yeah, exactly right. So to vote, use your QR code, which is right there on the screen, or you can text the library, Caltech library, to 37607. 37607. So Caltech library is right, says it right there. Okay. The what? The polls are blocked. The polls are blocked. Tommy, I can't. Next slide.
The poll is now unlocked, right?
Oh, you can sit down. Yeah. Just remember the letters. Very good. Oh, here we go. They are open. You have it on your screen? Oh, something's happening. We are still tabulating. Buffering. I think we should have some music. AMT, you got some music we can play? Ba 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 da ba ba da ba 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 da ba ba da ba. Ba da 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 da. Ba da da. Ba da da ba ba ba. Ba ba ba. Ba 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 ba. Oh, countdown. 7, everybody. 5, 4, 3, 2, 1. Yay. We are unlocking the voting. Live voting is happening and is being displayed on the screen. And one of these lucky grad students will become the Dana Roth People's Choice Award. Oh. Oh.
Does it say? Oh,
is that it?
Yeah.
Should I tell everyone?
Yeah.
Or should I have Stephen tell everyone?
You should.
Or should I have Becca? Okay. Okay, are you ready? Yes. Someone's like, okay, let's get on with this. All right, and the congratulations, Alex Chung, superpowers of the mind, harnessing the nervous system for regeneration. Congratulations. Wow. All right, Stephen, are you going to come up here? Are we ready for the winners? Have the winners? Oh. Uh-oh. Something's happening.
My name is Henry Lester, and I'm option representative for the neurobiology option. Alex is a member of that option. Clearly, this is completely ad hoc. Alex, you have a job. You and I will talk later. You're going to help recruit our next neurobiology faculty member.
First of all, thank you to all of you. It was inspiring. It was amazing. Very, very impressive. Thank you very much. So now for the big moment. I get to announce the third, second, and first place winners. Now, third place winner is Victor Vescu, How Faults Annoy Their Neighbors. The second place winner is Mike Greck McKon. Oceans and volcanoes. And the first place winner of the 2025 3MT competition is Hannah Dion Kersner. So thank you to all of tonight's participants, to our esteemed judges, and to our generous sponsors. And thank you all for attending this evening. We look forward to seeing you all in person at next year's Caltech 3MT competition. And for those of you who are joining us tonight, we have some light refreshments in the Chen breezeway.